Hi, my name is Muhammad Afiq Ayman Hassan. I will be presenting microstructural and elemental analysis of laser Wobble welds in ultra-thin stainless steel sheets SS304. These are the table of contents for the current presentation.
What is the motivation and industrial relevance of this study? Laser welding is considered as an advanced type of welding, and it is widely used in industries of EV batteries, fuel cell assemblies, and also medical devices. Laser welding promises precision welding compared to conventional welding that has limitations of thermal distortion and also lack of precision in thin materials. Laser welding overview. Some of the proven benefits of laser microwelding are it provides high energy density and small heat affected zone. It provides accurate penetration control, and it is ideal for foils, wires, and microcomponents. This is a diagram of laser welding schematic. Research background. The material of interest in this study is thin stainless steel SS304 foils. Stainless steel is known for its high strength, corrosion resistance, and also formability. Stainless steel is widely used in PEM fuel cells and also EV battery packs. The figures show thin stainless steel application on battery and also on fuel cell bipolar plate. What are the challenges in welding thin stainless steel? The first challenge is risk of overheating can lead to burn through. Second, oxidation resulting in oxide inclusions and porosity. And last but not least, high sensitivity to joint alignment and weld pattern. All of these require critical need for precise control of welding parameters to ensure weld integrity. As you could see on this figure, it shows a few types of welding defect that commonly happen in welding. The first literature review is by E. Esunkeo et al. In 2009, and based on their studies, it showed that fiber laser proved to be the best method compared to the other laser welding method. And also, fiber laser allows the highest speed with a lowest cost compared to other type of laser welding method. Second literature review is about wobble welding technique. So wobbling is proven to reduce distortion. Wobbling uses circular or figure-8 path to improve heat distribution, and it proved to result in less angle distortion in thin SS304, and as a consequence, it will improve joint strength and also stability of the weld.
Here is a literature review table from which we can get the research gaps.
Research gaps identified in this study are there are limited studies on low power laser welding of 0.1 mm SS304, and also there is limited studies on detailed microstructural and elemental comparison.
We laser welded samples SS304, 1 mm and 1 micrometer using wobbling technique, and testing of the different parameters such as wobbling diameter, power and frequency were carried out while keeping other parameters constant. Here is a range of parameters that were used in the experiment. The samples were after laser welding grounded and polished subsequently with diamond compound and colloidal silica for mirror surface finish. After that, the sample were section mounted, and the specimen post etching were sent to SMEDX for microstructural and elemental analysis. So moving to the results, here are different parameters from 1 to 15 that were laser welded with different parameters, and then we have got the views of the welded specimen for all the samples. Out of these 15 samples, 2 were selected for SEM and EDX analysis. So the samples that were selected were based on least defect and more defect samples corresponding to sample number 1 and sample number 2. Sample number 1 was laser welded at 80% power, yielding a high quality weld aspect ratio of 0.37 with minimal porosity, and we can see revealed uniform grains, clear fusion lines and minor micro voids, which is consistent with strong S304 joint integrity. But sample 2 was welded at higher power and low frequency, which resulted in wider aspect ratio, and the microscopy revealed more porosity and irregular grain structure in the fusion zone, suggesting less optimal thermal control compared to sample number 1. EDX analysis of the sample shows that the base plate maintains typical SS304 composition comprising of iron 65%, chromium 17 and nickel 7% with no oxygen detection. But as we do the welding in the fusion zone in sample B, we observe that there is a slight chromium nickel depletion, chromium 17 and nickel 6.4% with Fe increasing to 67.2%, suggesting minor elemental distribution or redistribution during welding. While the oxygen appears in the fusion zone, its level remains significantly lower than in the second sample that we will look in the next slide. So in sample 2, EDS analysis reveals significant oxidation and oxygen concentration peaking in the fusion zone while absent in the base plate. Iron dominates at 47.56%, but chromium depletion and nickel loss confirm severe oxidation during welding process. Why nickel loss matters? Nickel oxidation degrades chromium SS304 corrosion resistance, and this can be mitigated by employing shielding gas such as argon or other gas to suppress oxygen ingress. So comparing the sample number 1 and sample number 2 EDX, sample number 1 maintained better composition control with only slight chromium nickel depletion and minimum oxygen uptake. But sample number 2 suffered severe oxidation, high O2 levels, almost significant amount of nickel loss and greater chromium depletion. Elemental distribution was more pronounced in sample 2 than compared to sample 1. It shows that process parameters for sample number 1, lower power and high frequency, might have yielded better oxidation resistance, and that these samples are very sensitive to the laser parameters. So in the conclusion, we successfully laser welded SS304 sheets 100 micrometer and 1 micrometer using the laser wobbling technique. Sample 1 showed a controlled weld with low defects, while sample 2 had cracks and porosity due to excessive heat, making it more unreliable. In future research, I think further parameter testing should be carried out and optimization is recommended.